Welcome. Tonight we fall, not in fear, not with urgency, not toward anything that could harm you. We fall the way starlight falls, slowly, silently, toward the most mysterious objects the universe has ever made. Black holes. They are not the monsters science fiction imagined. They are not destroyers lurking in the dark waiting for something to consume. They are something far stranger, far quiet, far more beautiful than any story ever told about them. They are places where space itself curves completely inward, where time slows to a whisper and then almost stops, where the laws of the universe reach their absolute edge and simply stop making the demands they make everywhere else. They are the universe's deepest secret, its most patient mystery, its darkest and most extraordinary creation. And tonight, at this slow and unhurried pace, we are going to drift toward them together, not close enough to feel their pull, not close enough to be affected by their gravity in any way at all, just close enough to understand, and in understanding, to wonder. So let your body settle now. Feel the surface beneath you receiving your weight completely. Let your arms fall open at your sides. Let your shoulders drop away from your ears. Let the muscles around your eyes release whatever they have been holding all day. Take a breath in, slow and full. Black holes have been waiting billions of years to share their secrets. Tonight, you finally have time to listen. Let us begin. A black hole is not a hole. This is the first and most important thing to understand about them. And once you truly absorb it, everything else about black holes becomes more interesting, more accessible, and somehow more calming. A black hole is not an empty space, not a void, not a gap torn in the fabric of the universe, not a cosmic drain pulling everything toward nothing like water spiraling down a bathtub. A black hole is an object, a real, physical, extraordinarily massive object, one of the most substantial concentrations of matter in the known universe, made of the same fundamental particles as everything else, governed by the same laws of physics that govern stars and planets and the atoms in your body. It forms when a star so massive that our own sun would look modest and unremarkable beside it, exhausts the nuclear fuel at its core and collapses inward under the irresistible force of its own gravity. The collapse happens with extraordinary speed. A star that burned steadily for millions of years, compressed in less than a second into something unimaginably small and dense. What remains after the collapse is a concentration of mass so extreme, so compressed, that space itself curves completely around it. Not partially, not dramatically, but with some escape possible. Completely, in every direction, without exception. The gravity produced by this concentration of mass is so powerful that nothing can move fast enough to escape it. Not rock, not gas, not radiation of any kind, not even light. And light moves at 300,000 kilometers per second, the fastest speed at which anything in the universe is permitted to travel. If light cannot escape, nothing can. That is why a black hole appears black. Not because nothing is there, not because it is an absence or a void, but because the light that falls into it never comes back out. The object is present, massive, real, genuinely and substantially there, but invisible to every telescope and every instrument because it produces no light of its own and reflects no light that could ever reach an observer. We detect black holes not by seeing them directly, but by watching everything around them. Stars orbiting a black hole move at velocities that would be impossible if the black hole were not there. Gas falling toward a black hole heats to millions of degrees and radiates brilliantly in the moments before crossing the point of no return. Light from distant objects passing near a black hole bends around it, creating rings and arcs and distorted images that would not exist without the invisible mass at the center. The black hole announces itself through everything it does to its surroundings, while remaining itself perfectly, completely, invisibly dark. There is something genuinely meditative about that quality, the most massive objects in the galaxy making no sound, producing no light of their own, known only by their influence on everything around them, present everywhere in their effects, invisible in any direct observation. The nearest black hole to Earth is approximately 1,000 light-years away. Its gravity has no measurable effect on our planet, on our solar system, on anything we experience in any aspect of daily life. It drifts in the dark of the galaxy at a distance so vast that it might as well not exist for any practical purpose. It is simply there, patient and still, the way all genuinely ancient things are patient and still, not waiting for anything, not threatening anything, simply occupying its place in the slow-turning structure of the galaxy, as it has for billions of years. Not every star becomes a black hole. This is worth saying clearly, because it places black holes in their proper context and makes them feel less like universal threats and more like what they actually are: rare endpoints of specific and extraordinary stellar lives. Our own sun will not become a black hole, not because it will live forever, but because it lacks the mass required for that particular ending. When the sun eventually exhausts its hydrogen fuel, in approximately 5 billion years, the process will be gradual, even gentle by cosmic standards. The outer layers will expand slowly outward as the core contracts. The sun will swell into a red giant, large and luminous but cool at the surface, possibly expanding far enough to engulf Mercury and Venus, possibly reaching toward Earth. But eventually, after perhaps a billion years as a red giant, the outer layers will drift away into space as a slowly expanding cloud of glowing gas called a planetary nebula. Colorful, delicate, beautiful in the way that endings can sometimes be beautiful. What will remain at the center is a white dwarf, a dense sphere roughly the size of Earth but containing the mass of the sun, made mostly of carbon and oxygen pressed into a crystalline structure by immense gravity, glowing initially from residual heat, and then cooling, across billions of years, into darkness. A quiet ending, slow, without violence. But for stars much more massive than our sun, the story is completely different. A star 10 times, 20 times, 50 times the mass of our sun burns through its fuel at a rate that scales dramatically with mass. The more massive the star, the hotter the fusion at its core, the faster the fuel is consumed, the shorter the life. A star 100 times the mass of our sun burns so furiously that it exhausts its hydrogen in just a few million years. A few million years. Where our sun has 10 billion years of main sequence life, these stars have a few million, brief and extravagant, the most profligate spenders in the stellar economy. While the hydrogen lasts, the star exists in a state of magnificent equilibrium. Nuclear fusion at the core, generating energy that pushes outward against gravity. Gravity pulling inward against the pressure of fusion, neither winning. A balance sustained across millions of years. Then the hydrogen at the core runs low. The core begins to contract, heats further, reaches temperatures sufficient to fuse helium, then carbon, then oxygen, then silicon, each stage producing less energy than the last, each stage lasting a shorter time. The star burning through heavier and heavier fuel in less and less time. The final stage ends with iron. Iron is the end of the line for nuclear fusion energy production. Unlike lighter elements, iron does not release energy when fused. It absorbs it. A core of iron accumulates, gravity pulls on it, and with no fusion energy to resist, the core collapses. In less than 1 second, the collapse is so sudden and so complete that the rebounding shockwave tears the rest of the star apart. A supernova, briefly shining with the luminosity of a billion suns, scattering stellar material across light years of space, and at the center, in the sudden quiet after the explosion, a black hole. Every black hole has a boundary, not a physical surface, not a wall or a membrane you could press your hand against. Not a visible edge that would appear different from the space around it. A boundary, nonetheless. Real and absolute, and in its own way more definitive than any physical barrier in the universe. Astronomers call it the event horizon. The name carries its meaning precisely. An event horizon is the surface beyond which events cannot influence an outside observer. Whatever happens inside the event horizon produces no signal, no light, no radiation, no gravitational wave. No information of any kind that can ever cross back to the universe outside. Inside the event horizon, events occur, things happen. The laws of physics continue to operate, but the record of those events is sealed from the rest of the universe, permanently and completely. The event horizon of a stellar mass black hole, One that formed from a single massive star might have a radius of only a few kilometers, a sphere that would fit comfortably inside a city, containing the mass of multiple suns. The event horizon of a supermassive black hole, billions of times the mass of our sun, extends across a region the size of the solar system or larger. The radius of the event horizon is directly proportional to mass. Double the mass, double the radius. The relationship is clean and simple, nature being unusually straightforward. Now consider what it would be like to approach one. If you were traveling through space toward a stellar mass black hole, with no thrust, simply falling freely toward it under gravity, something remarkable would happen as you neared the event horizon. From your own perspective, nothing unusual. You would feel weightless, because you are in free fall. Every part of your body accelerating equally toward the black hole. No sensation of being pulled in any direction. The gravitational field would feel perfectly calm and uniform as long as the black hole was sufficiently massive that tidal forces across your body were small. You would feel yourself falling, but free fall feels like floating. And then you would cross the event horizon, still feeling nothing unusual. No barrier, no resistance, no sensation of transition. You would simply be inside, in the region from which no signal can escape. And the universe you left behind would be sealed from you, as completely as if it had ceased to exist, from the perspective of someone watching you fall from a great distance. The story looks entirely different. They would watch you approach the event horizon and appear to slow down, not because you are actually decelerating, but because the light you emit takes longer and longer to escape the deepening gravity well. Your image would appear to freeze at the boundary, growing dimmer, redder, fainter, an echo of you preserved at the threshold, dimming over an infinite time but never fully disappearing. Two perspectives, one falling person, two completely different stories. The universe comfortable with this duality, the way the universe is comfortable with many things that seem contradictory, but are simply the consequences of consistent physical law applied in different circumstances. The universe is saturated with black holes, far more so than was suspected even a few decades ago, before gravitational wave astronomy opened an entirely new way of detecting them, before deep surveys of stellar populations revealed how common the conditions for black hole formation truly are. The Milky Way galaxy alone is estimated to contain somewhere between 10 million and 1 billion stellar mass black holes. The broad range of that estimate reflects the difficulty of counting objects that are invisible by definition. The most commonly cited figure, based on models of stellar evolution and the rate of supernova events throughout the galaxy's history, is approximately 100 million. 100 million black holes, drifting invisibly through the stellar disk of our galaxy, scattered among 300 billion stars across a structure 100,000 light-years wide, most of them completely isolated, in regions of space with nothing nearby to reveal their presence. No gas clouds to heat and glow as they fall inward. No companion stars to perturb, simply drifting. Patient, silent, invisible, if you could see them, if they somehow emitted light of their own. The galaxy would look dramatically different on a clear night, but they do not. And so the sky appears to contain only the stars, while 100 million dark remnants drift quietly among them. The nearest known black hole to Earth is V616 Monocerotis, located approximately 3,300 light-years away. It is a binary system, the black hole orbiting with a companion star, the gravitational interaction between them revealing what would otherwise be invisible. 3,300 light-years. The light you see from it tonight left its location 3,300 years ago. At that time, civilizations now considered ancient were still young. The Bronze Age was ending. The Iron Age was beginning. The Trojan War was a recent memory. That light has been traveling toward Earth for all of recorded human history, and the black hole itself drifts in its slow orbit, 3,000 light-years away, its gravity having no measurable influence on Earth, its existence relevant to us only as an object of contemplation. Now scale this outward. The observable universe contains approximately 2 trillion galaxies, each one containing its own population of black holes, ranging from small irregular galaxies with millions to giant ellipticals with hundreds of billions. The estimated total number of stellar mass black holes in the observable universe exceeds 10 to the power of 18, a 1 followed by 18 zeros, a quintillion black holes, and additionally, the supermassive black holes at the centers of virtually all large galaxies, each one millions to billions of times the mass of the Sun. The universe has been producing black holes since its earliest chapters. The first massive stars formed within the first few 100 million years after the Big Bang lived their brief, brilliant lives and collapsed into black holes that still exist today, 13 billion years later, 13 billion years old, and still as dark, as quiet, as perfectly still as the day they formed. There is a class of black hole that defies easy description, not because the physics is especially unclear, but because the scale is so far beyond any human reference point that the numbers require a moment of quiet to appreciate. Supermassive black holes, objects containing not just a few times the mass of the Sun, not even a few thousand times, but millions, hundreds of millions, in the most extreme cases known, tens of billions of times the mass of our Sun, at the center of the Milky Way, our own galaxy, 26,000 light-years from Earth, sits a supermassive black hole designated Sagittarius A star. Its mass is approximately 4 million times that of our Sun, 4 million suns worth of mass, compressed within a region smaller than our solar system. Its event horizon would fit within the orbit of Mercury around our Sun. Sagittarius A star is the gravitational center around which the entire Milky Way slowly orbits. Every star in the galaxy, every cloud of gas and dust, every nebula and cluster and drifting remnant, all of them tracing their slow paths around this central mass. The galaxy has been orbiting it for billions of years, and Sagittarius A star has spent most of that time doing what it is doing right now, sitting quietly at the center, not actively consuming large amounts of material, not producing dramatic jets of energy, simply present, massive. The still point around which everything turns, by supermassive standards. Sagittarius A star is modest. The galaxy Messier 87, an enormous elliptical galaxy in the Virgo cluster some 53 million light-years from Earth, contains a supermassive black hole approximately 6.5 billion times the mass of our Sun, 6.5 billion solar masses. If Sagittarius A star were the size of a basketball, the black hole at the center of M87 would be the size of a building. In April of 2019, an international consortium of astronomers operating 8 radio telescopes distributed around the world synchronized them into an effective single instrument the diameter of Earth, pointed this extraordinary array at M87, and captured the first direct image of a black hole ever obtained. The image showed a glowing ring of superheated gas, orbiting just outside the event horizon, heated to billions of degrees by compression and friction as it spiraled inward, glowing brilliantly at radio wavelengths. And at the center of that glowing ring, a shadow, a circular region of darkness produced by the fact that light from behind the black hole was being bent around it, while light from within the event horizon could not escape. The shadow of the event horizon itself. The darkness at the center of that image is genuinely the darkest thing ever directly imaged by human instruments, surrounded by the brightest, separated by the sharpest possible boundary. When the scientists who had spent years working toward that image first saw it appear on their computer screens, many of them wept. Time is not what it appears to be. This statement is not philosophy, not metaphor, not the kind of poetic observation that scientists sometimes allow themselves at the edges of their work. It is one of the most precisely tested, most thoroughly confirmed, most mathematically exact results in the entire history of physics. Time passes at different rates in different gravitational fields. Albert Einstein predicted this in 1915, in his general theory of relativity, before the technology existed to test it, before atomic clocks existed, before satellites existed, before GPS existed. He predicted it from pure mathematics. From the geometric structure of his equation, the stronger the gravitational field, the slower time passes. Near the surface of the Earth, clocks at sea level run very slightly slower than clocks at higher altitudes, because sea level is deeper in Earth's gravitational field. The difference is tiny, approximately 45 microseconds per day between a clock at sea level and a clock in orbit several hundred kilometers above. 45 microseconds per day sounds negligible, but multiply it across the operation of the GP's satellite network, which must coordinate positions to meter-level accuracy, and those 45 microseconds per day would produce positioning errors of approximately 10 kilometers per day, compounding continuously, making GPS useless within weeks. GPS works because engineers continuously correct for gravitational time dilation, every day, every hour, every navigation calculation that anyone makes on Earth. The correctness of Einstein's 1915 prediction is built into the infrastructure of modern civilization. Near a black hole, the same effect becomes extreme beyond any everyday reference. At the event horizon of a black hole, time dilation becomes infinite. A clock at the event horizon, from the perspective of a distant observer, would appear to stop completely, just outside the event horizon. Time would pass almost infinitely slowly relative to time far away, if you could somehow hover just above the event horizon of a large black hole, protected by some impossible technology from tidal forces and radiation, and remain there for what felt to you like 1 hour when you returned to the distant universe. Thousands of years would have passed there. Your 1 hour, their millennia, both equally real, both equally valid, both consequences of the same physics that makes GPS work and that governs the behavior of every massive object in the universe. Time is not a universal river flowing at the same rate everywhere. It is a landscape, shaped by mass, moving quickly in the open flat spaces far from gravity, moving slowly near massive objects, and near a black hole, moving at a pace so slow that from a sufficient distance it appears to stop. The universe has been quietly doing this since the beginning. At the center of every black hole, according to the mathematics of general relativity, sits a singularity. This word carries enormous weight in physics and enormous uncertainty. A singularity is defined as a point of zero volume and infinite density. The entire mass of the black hole compressed into a region of space that has no size, no extent, no dimensions whatsoever, zero volume, with finite mass, infinite density. Because density is mass divided by volume, and any finite mass divided by zero volume produces a mathematical infinity. These numbers, 0 and infinity, are not approximations or simplifications. They are the precise outputs of Einstein's field equations when those equations are applied to the conditions inside a black hole. The mathematics produces them exactly, and this is precisely why physicists do not believe they represent physical reality. In physics, when a well-tested theory produces an infinite answer, it is almost universally understood to mean that the theory is being applied beyond its domain of validity, that something is missing from the description, that a more complete theory would replace the infinity with something finite. General relativity is extraordinarily well tested in every accessible region of the universe. Its predictions have been confirmed to remarkable precision in every situation that can be tested. The orbit of Mercury, the bending of light by the sun, gravitational waves from merging black holes, the expansion of the universe, time dilation near massive objects. But general relativity does not incorporate quantum mechanics, and at the extreme densities near a singularity, quantum mechanical effects become important. Effects related to the fundamental granularity of nature at its smallest scales. Effects that general relativity completely ignores. Quantum mechanics and general relativity are the two most successful theories in the history of physics, each tested to extraordinary precision within its domain, and they are fundamentally incompatible with each other in their current mathematical frameworks. The singularity is where this incompatibility becomes impossible to ignore. Physicists have been working for decades to construct a theory of quantum gravity, a framework that incorporates both the large-scale geometric structure of general relativity and the quantum mechanical behavior of matter at small scales. String theory attempts this. Loop quantum gravity attempts this. Several other frameworks attempt this. None has yet produced a complete and universally accepted result. The singularity remains genuinely unsolved, the center of every black hole in the universe. every one of the hundreds of millions in our galaxy, and the quintillion scattered across the observable cosmos, each one containing at its heart a question that the greatest physicists of the past century have not yet answered. The universe has hidden something at the darkest point of its darkest structures, and it is waiting, patiently, as it always waits, for the understanding that will one day arrive. String theory proposes that the fundamental constituents of reality are not point particles but tiny vibrating strings of energy. In some versions of the theory, the singularity is smoothed out by the finite size of these strings, which cannot be compressed below a minimum scale. Loop quantum gravity proposes that space itself is quantized, made of discrete units below which no further division is possible. In this framework, the singularity is replaced by an extremely compressed but finite state, from which the interior of the black hole continues to evolve. Both approaches remain incomplete. Both remain contested, but both represent the extraordinary human effort to reach beyond the limits of current understanding, toward a description of nature that is complete. The singularity is not a failure of physics. It is an invitation. The universe pointing towards something it has not yet revealed, waiting with the patience it has demonstrated across 13 billion years of cosmic history for the question that will finally open the door. In 1974, a young physicist named Stephen Hawking made a discovery so unexpected, so counterintuitive, so completely surprising even to him, that it changed the way scientists think about black holes forever. Black holes, he showed, are not entirely black. They glow, not with any light visible to the human eye, not with any radiation detectable by current instruments, but in principle, according to the mathematics of quantum mechanics applied to the boundary of the event horizon. Black holes emit a faint, steady, thermal radiation. This radiation is now called Hawking radiation in his honor. To understand where it comes from, you have to understand something about the quantum nature of empty space. In classical physics, empty space is simply empty. Nothing there. A true vacuum containing no energy and no particles. But quantum mechanics reveals that so-called empty space is not actually empty at all. At the quantum level, space is filled with a constant, seething activity. Pairs of virtual particles spontaneously appearing from the vacuum energy. One particle and one antiparticle, born together, existing for a vanishingly brief moment, and then annihilating each other and disappearing back into the vacuum. This happens everywhere, constantly, even in the space you are occupying right now. Pairs of virtual particles flickering into and out of existence billions of times per second, in every cubic centimeter of space around you, under normal circumstances. These virtual pairs always annihilate. They exist too briefly and with too little energy to have any measurable effect. But at the event horizon of a black hole, something different can happen. A virtual pair appears near the event horizon. One particle lands just inside the horizon, the other just outside. The one inside is captured by the black hole. The one outside, suddenly separated from its partner before annihilation can occur, is forced to become a real particle, and it escapes into space as genuine radiation. To conserve energy, the particle that fell into the black hole carries negative energy, effectively reducing the black hole's mass by a tiny amount. The result, over time, is that the black hole slowly loses mass, radiating it away as Hawking radiation, particle by particle. For a stellar mass black hole, the temperature of this radiation is so incredibly low, billionths of a degree above absolute zero, that it is completely undetectable against the cosmic microwave background radiation that fills the universe. For a supermassive black hole billions of times more massive, the temperature is even lower, but the process continues, slowly, over timescales so vast that the word astronomical becomes inadequate. A stellar mass black hole would take approximately 2 × 10⁻�67 years to evaporate completely through Hawking radiation, 2 followed by 67 zeros. For reference, the current age of the universe is approximately 14 billion years, a number with 10 digits. The evaporation timescale of a stellar mass black hole has 68 digits. In the unimaginably distant future, long after the last stars have burned out, and the last white dwarfs have cooled to invisibility. Long after the galaxies have dissolved into isolated remnants drifting through an expanding void, the black holes will remain. Slowly, over timescales that dwarf the current age of the universe by factors that language cannot express. They will evaporate, and when the last black hole in the observable universe finally radiates away its last particle, what remains will be the faintest possible glow, the final light of the last black hole, gradually diminishing into the deepest dark the universe will ever know. Hawking himself called it one of the most beautiful results in theoretical physics, a place where quantum mechanics and general relativity overlap and produce something neither theory could predict alone. The idea that black holes radiate is counterintuitive at the deepest level. The very definition of a black hole is that nothing escapes it. And yet here is a rigorous quantum mechanical calculation, showing that something does escape. Not from inside the event horizon, but from the quantum fluctuations at the boundary itself. The horizon is not a passive edge. It is an active participant in quantum processes. What happens to information when it falls into a black hole? This question has occupied some of the greatest minds in theoretical physics for nearly 50 years. And it remains, as of this moment, one of the most profound unresolved problems in science. The question sounds deceptively simple, but its implications reach to the very foundation of how the universe is structured. In physics, information is not merely a human concept. It is a precise technical quantity, the complete description of the physical state of a system. Every particle, every field, every quantum property. One of the most fundamental principles in quantum mechanics, called unitarity, states that information is never created or destroyed. The physical laws governing the universe are information preserving. If you knew the complete state of a physical system at any moment, you could in principle calculate its state at any other moment, past or future. Information does not disappear from the universe. But what happens when matter falls into a black hole? The matter carries information. Its quantum state is part of the total information content of the universe. When it crosses the event horizon, it becomes inaccessible to the outside universe. That is simply what the event horizon means. And when the black hole eventually evaporates through Hawking radiation, the radiation it emits appears to be completely random, thermal, carrying no information about what fell in. A star fell in. The star carried enormous amounts of information, the positions and momenta and quantum states of every particle it contained. After evaporation, that information appears to be simply gone. But the laws of quantum mechanics say information cannot be destroyed. This contradiction is called the black hole information paradox. Stephen Hawking argued for decades that black holes do in fact destroy information, that they represent a genuine exception to the principle of unitarity. Most other physicists, including his close friend and frequent sparring partner Kip Thorne, argued that information must somehow be preserved, that Hawking radiation must carry information encoded in subtle correlations that make it appear thermal, but are not truly random. The argument went on for decades, with no resolution, growing into what physicists sometimes called the black hole wars. In his later years, Hawking revised his position, accepting arguments from string theory and the holographic principle that information is indeed preserved, somehow, in ways that are not yet fully understood. But how exactly the information escapes, what form it takes in the outgoing radiation, by what mechanism it is preserved through the Hawking evaporation process, these questions do not yet have agreed answers. The universe has kept this secret carefully, at the intersection of its two greatest theories, where quantum mechanics and general relativity are forced to confront each other most directly. It waits, with its characteristic patience, for the understanding that has not yet come. The stakes of the information paradox extend beyond black holes. If information can truly be destroyed, then the universe is fundamentally different from what quantum mechanics describes. The principle of unitarity is not a minor technical detail. It is load-bearing for the entire structure of quantum theory. Without it, probabilities in quantum mechanics would not sum to one. The predictive framework that underlies all of modern physics would be compromised. This is why so many physicists refuse to accept that black holes destroy information, and so the search for the mechanism of information preservation continues. Hidden somewhere in the mathematics of quantum gravity, waiting to be found, gravity does not pull on you as a single object. It pulls on every part of you individually, on every atom, every molecule, every cell, each one experiencing the gravitational field at its own particular location, near the surface of the Earth. The difference in gravitational pull between your feet and your head is so small as to be completely unfelt. Your feet are very slightly closer to the center of the Earth than your head, and they experience very slightly more gravitational pull. But the difference is so minuscule that your body experiences no sensation from it whatsoever. These differential gravitational forces are called tidal forces, named after the tides, which are caused by the slightly greater gravitational pull of the Moon on the side of Earth facing the Moon compared to the side facing away. Near a black hole, tidal forces become the primary danger. For a small black hole, a stellar mass black hole with an event horizon only a few kilometers across, the tidal forces at the event horizon are catastrophic. As you approached such a black hole, the gravitational pull on the part of your body closest to it would be dramatically stronger than the pull on the part farthest from it. The difference in force across the length of a human body, even at considerable distance, would be enough to stretch you, to pull you into an increasingly elongated shape. Physicists call this process spaghettification, not a particularly elegant term for an extraordinarily dramatic phenomenon, but the process is real. As you fell toward a stellar mass black hole, you would be stretched lengthwise and compressed sideways, the process accelerating as you got closer, until long before you reached the event horizon. You would have been pulled apart into a thin stream of particles, each one following its own geodesic toward the singularity. However, for a supermassive black hole, the situation is dramatically different. The tidal forces at the event horizon of a black hole scale inversely with the square of the mass. The more massive the black hole, the weaker the tidal forces at the event horizon. For a black hole of Sagittarius A star's mass, 4 million solar masses, the tidal forces at the event horizon are already much gentler than at the event horizon of a stellar mass black hole. For a supermassive black hole of several billion solar masses, the tidal forces at the event horizon are so gentle that a human body could cross it without experiencing any discomfort at all. You would fall through the event horizon of the most massive black holes in the universe, feeling nothing, the most extreme boundary in nature, passed in perfect comfort, with no sensation to mark the most consequential threshold in the cosmos, the universe arranging for the gentlest possible ending, at the edge of the darkest possible place. The term spaghettification was coined informally by astrophysicists and has become standard in popular science discussions of black holes. It captures something real, as tidal forces stretch an infalling object. The process is gradual at first, almost imperceptible at large distances, then increasingly dramatic as the object approaches the event horizon of a small black hole. The stream of particles that had once been a coherent object spirals inward toward the singularity, each particle following the geometry of space-time toward the center. The object destroyed not by collision or explosion, but by the simple mathematical consequence of differential gravity. In the early universe, the black holes at the centers of galaxies were not quiet. They were feeding, actively and voraciously consuming the enormous quantities of gas that surrounded them in the dense, early cosmos, drawing it inward, heating it to billions of degrees as it spiraled into an accretion disk, and releasing energy in quantities so extraordinary that they can be seen across the full width of the observable universe. These feeding supermassive black holes are called quasars, short for quasi-stellar objects, named because when first discovered in the 1950s and 1960s, they appeared to be bright points of light, like stars, but with redshifts indicating they were billions of light years away, far too distant to be ordinary stars and far too bright. What astronomers had discovered, without initially knowing it, were the most luminous sustained objects in the universe. A single quasar can emit more energy than 1 trillion suns combined. 1 trillion suns. from a region no larger than our solar system. The energy comes from the accretion disk. Gas and dust and stellar material falling toward the black hole heats through compression and friction to temperatures of billions of degrees. It radiates across the entire electromagnetic spectrum, from radio waves to visible light to X-rays to gamma rays. The radiation jets outward along the axis of rotation in beams that can extend for millions of light-years into surrounding space. The most powerful quasars are so bright that they outshine the combined light of every star in their host galaxy by factors of hundreds or thousands. The galaxy itself, containing hundreds of billions of stars, is invisible against the blazing output of its central black hole. We see quasars across the entire observable universe. The most distant known quasars are seen as they were less than 1 billion years after the Big Bang, when the universe was less than 7% of its current age. This tells us something important about the history of black holes and galaxies. In the early universe, black holes were actively feeding. Quasars were common. The universe was a brighter, more turbulent, more energetically active place than it is today. As the universe aged, as the available gas was consumed or dispersed, the feeding slowed, the quasars dimmed. The supermassive black holes settled into the quiet dormancy we observe in most nearby galaxies today, including our own, Sagittarius A star, today so quiet and still at the center of the Milky Way, was almost certainly a quasar billions of years ago, blazing with the energy of 1 trillion suns, outshining the entire galaxy that was slowly forming around it. The quiet at the center of the Milky Way tonight is not the quiet of something that was never powerful. It is the quiet of something that has finished, that has settled, that has reached a kind of cosmic rest after an era of extraordinary activity. The quiet of something ancient that has earned its stillness. The power output of the most luminous quasars is so extreme that astronomers sometimes struggle to explain how the black holes feeding them accumulated enough mass to sustain such output. In the early universe, just a few 100 million years after the Big Bang, quasars are already observed with black hole masses of billions of solar masses. Growing to such sizes in so little time requires consuming matter at rates that push against theoretical limits, known as the Eddington limit. Some early quasars appear to have exceeded even this limit, growing faster than theory says should be possible, another mystery the universe has not yet fully explained. On September 14th, 2015, at 5:51 in the morning Eastern Time, 2 detectors, located in Livingston, Louisiana and Hanford, Washington, separated by 3,000 kilometers, registered a signal that had been predicted by theory for 100 years but never detected, a gravitational wave, a ripple in the fabric of space-time, produced by the merger of 2 black holes approximately 1.3 billion light-years away. The signal lasted less than 0.2 of a second. In that fraction of a second, the waveform carried the complete story of the merger. 2 black holes, each roughly 30 solar masses, had been spiraling toward each other for billions of years, their orbital separation shrinking imperceptibly slowly at first, then faster still, as they shed energy as gravitational waves and drew inexorably together. In the final fraction of a second before merger, they were orbiting each other at a significant fraction of the speed of light, each orbit taking milliseconds, each orbit bringing them closer, and then they merged. In that moment, they released energy equivalent to approximately 3 solar masses, converted directly and instantaneously from mass into gravitational wave energy, 3 times the mass of our Sun, converted into pure spacetime distortion in a fraction of a second. More energy released in that instant than all the stars in the observable universe emit in the same period of time, and the resulting ripple in space-time propagated outward at the speed of light in every direction for 1.3 billion years. This ripple traveled through the universe, through galaxy clusters, through the vast cosmic voids, through the expanding fabric of space itself, until it reached Earth, where it caused the instruments at LIGO to shift by a distance 20 times smaller than the diameter of a proton. 20 times smaller than a proton. The most sensitive measurement ever made by any human instrument, detecting the whisper of an event that happened when multicellular life had barely begun on Earth. The signal lasted less than 1/5 of a second. It contained enough information for scientists to determine the masses of the two black holes, the mass of the final merged black hole, the amount of energy radiated, the approximate distance to the merger, and the fact that it was consistent with general relativity to extraordinary precision. Einstein predicted gravitational waves in 1916, 1 year after completing general relativity, but he doubted they would ever be detectable. The effects were simply too small, too fleeting, too subtle. He was wrong about the detection. 100 years after his prediction, we heard the universe ring. The detection opened an entirely new window on the universe. For the first time in history, astronomers could observe cosmic events not through light or electromagnetic radiation, but through the distortion of space-time itself. In the years following the first detection, LIGO and its partner detector Virgo detected dozens of additional black hole mergers. Each detection a new chapter in humanity's expanding conversation with the cosmos. Each one a message that traveled for millions or billions of years to reach us. Each one confirming that Einstein's equations, written in 1915, describe reality with breathtaking accuracy. Black holes and galaxies are not separate phenomena that happen to coexist. They are deeply, intimately, inextricably connected in ways that astronomers are still working to fully understand. The most fundamental connection is the one that exists between every large galaxy and the supermassive black hole at its center. Every large galaxy that has been studied in sufficient detail. Every elliptical galaxy. Every spiral galaxy large enough to contain a significant central bulge has been found to harbor a supermassive black hole at its core. Not some of them, not most of them, every one. And the mass of the central black hole correlates precisely with properties of the galaxy itself, specifically with the mass of the central bulge of stars that surrounds it. The ratio is remarkably consistent. The black hole always contains approximately 0.1% of the total mass of the surrounding stellar bulge. This relationship is called the M-sigma relation, and it implies that the growth of the black hole and the growth of the galaxy are somehow coordinated. Somehow the black hole knows how large the galaxy is, and the galaxy knows how large the black hole is, but they are separated by enormous distances. The black hole occupies a region at the very center, while the stars of the bulge extend across thousands of light years in every direction. How does information about one reach the other? How does the coordination happen? The leading explanation involves feedback. When a supermassive black hole is actively feeding, as a quasar, it produces enormous amounts of energy. Not just light, but jets and winds of energetic particles that extend outward from the galactic center into the surrounding galaxy. These jets and winds can heat the gas that would otherwise condense to form new stars. They can push gas out of the galaxy entirely, regulating the supply of material available for both star formation and further growth of the black hole itself. The black hole acts as a regulator, a thermostat, preventing the galaxy from forming stars too quickly by injecting energy into the surrounding gas when feeding is active, and allowing star formation to proceed when feeding is quiescent. And the galaxy in turn regulates the black hole by controlling the supply of gas that reaches the center. The two systems, separated by thousands of light years, evolving together across billions of years, each shaping the other, each responding to changes in the other. The black hole and the galaxy are not separate objects that happen to occupy the same space. They are partners, engaged in a relationship that has been ongoing since both formed in the early universe. Each one part of the other's story, neither one comprehensible without the other. Between the white dwarfs and black holes that mark the endpoints of stellar evolution, there exists a third possibility, one that is in some ways even stranger than either, a neutron star. When a massive star collapses at the end of its life, but its core mass falls in a specific range, not light enough to become a white dwarf, not heavy enough to collapse all the way to a black hole. The collapse stops at an intermediate point. Where it stops is extraordinary. The collapse is halted by neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from being compressed beyond a certain density. The result is an object approximately 20 kilometers across, containing between 1.5 and 2 times the mass of our Sun, 20 kilometers across. A sphere that would fit comfortably within a major city, containing more mass than the Sun. A single cubic centimeter of neutron star material, a volume the size of a sugar cube, would weigh approximately 100 million tons on Earth. The surface gravity of a neutron star is approximately 200 billion times stronger than Earth's surface gravity. If you placed a marshmallow on the surface of a neutron star from a height of 1 meter, it would impact with the energy of an atomic bomb. The magnetic fields of neutron stars are among the most intense in the universe. A typical neutron star has a magnetic field 1 trillion times stronger than Earth's. And yet, for all their extraordinary properties, neutron stars are stable. They exist in a condition of equilibrium, sustained against further collapse by the quantum mechanical resistance of their neutrons to compression. An equilibrium sustained not by nuclear fusion as in a living star, not by electron degeneracy pressure as in a white dwarf, but by the fundamental quantum mechanical inability of neutrons to occupy the same state. The universe finding yet another way to say, this far, and no further. But there is a limit to neutron degeneracy pressure, a maximum mass above which even neutrons cannot resist collapse. This limit, called the Tolman-Oppenheimer-Volkoff limit, is estimated to lie somewhere between 2.5 and 3 solar masses. Below it, a collapsing core becomes a neutron star. Above it, nothing stops the collapse. The core continues inward, past neutron star densities, past any known form of stable matter, into a singularity, a black hole. The boundary between neutron star and black hole is one of the most dramatic thresholds in nature. On one side, an extraordinarily dense but stable and enduring object. On the other side, a point of infinite density and no extent, separated by a few tenths of a solar mass. The universe calibrating its outcomes to extraordinary precision. And this precision, this fine-tuned balance between the extremes of existence, is one of the most quietly astonishing features of the cosmos we inhabit. The discovery of pulsars in 1967 provided the first observational evidence that neutron stars actually exist. A pulsar is a rapidly rotating neutron star, emitting beams of electromagnetic radiation from its magnetic poles. As it rotates, these beams sweep through space like a lighthouse beam. If Earth lies in the path of the beam, we detect a regular pulse of radio waves with extraordinary precision. Some pulsars spin hundreds of times per second, their timing so regular that they rival the best atomic clocks on Earth. The first pulsar discovered was initially nicknamed LGM-1, for Little Green Men, because the signal seemed almost too regular to be natural. It was a neutron star, spinning in the dark with metronomic precision, one of the most precisely regular natural phenomena the universe produces. When matter falls toward a black hole, it rarely falls in a straight line. Almost everything in the universe carries some angular momentum, some rotation, some sideways motion relative to the object it is falling toward. And this angular momentum does not disappear. It is conserved, a fundamental law of physics maintaining it through every interaction. So, instead of falling directly inward, the infalling material begins to orbit, spiraling slowly toward the black hole in an ever-tightening path, colliding with other infalling material coming from slightly different directions, compressing, heating, building up into a flattened rotating structure that surrounds the black hole like a disk, an accretion disk. The accretion disk is one of the most energetically extreme environments in the universe, and one of the most visually extraordinary. As material spirals inward through the disk, it loses gravitational potential energy. That energy does not disappear. It converts into heat. The closer to the black hole, the more energy is released, the higher the temperature rises. In the outermost regions of an accretion disk, temperatures might reach millions of degrees. In the innermost regions, just outside the event horizon, temperatures climb to hundreds of millions or even billions of degrees. At these temperatures, matter does not emit visible light. It radiates primarily in X-rays, in some cases in gamma rays, wavelengths of light far more energetic than anything the human eye can detect. The accretion disk around a stellar mass black hole in a binary system, with a companion star feeding material into the disk, can be one of the brightest X-ray sources in the galaxy. The accretion disk around a supermassive black hole in a distant quasar, fed by vast quantities of infalling gas and disrupted stars, can outshine the combined light of every star in the host galaxy. All of this energy, all of this extraordinary luminosity, comes ultimately from gravity, from matter falling, from the same force that keeps you on the surface of the Earth right now, the same force that holds the Moon in its orbit, the same force that shaped the galaxy and drew the first clouds of hydrogen together to form the first stars. Gravity, converted to light by the simple act of falling, and at the innermost edge of the accretion disk, the material reaches the innermost stable circular orbit, the closest point at which matter can orbit the black hole without inevitably spiraling inward in a short time. Beyond this point, no stable orbit exists. Material crosses this boundary and falls quickly toward the event horizon, passing through in moments that represent, for anything that falls this far, a point of no return, not just in the sense of the event horizon, but in the practical sense that the journey to the singularity has become essentially inevitable. The innermost stable circular orbit depends on the spin of the black hole. For a non-rotating black hole, it sits at 3 times the Schwarzschild radius. For a maximally spinning black hole, it can approach the event horizon itself. This means that spinning black holes are more efficient engines of energy conversion than non-spinning ones. A maximally spinning black hole, consuming infalling matter through its accretion disk, can convert up to 42% of the rest mass energy of that matter into radiation before it crosses the event horizon. 42%, by comparison. The nuclear fusion that powers the Sun converts less than 1% of mass into energy. Black holes are the most efficient energy conversion mechanisms in the known universe, powered entirely by gravity, powered entirely by falling. Most stellar mass black holes drift through space in complete isolation. No companion, no infalling material, no accretion disk, no radiation, simply dark, cold, invisible, moving slowly through the galaxy like ghosts of stars that burned out long ago. These isolated black holes are extraordinarily difficult to detect, with no source of radiation to betray their presence. Only their gravitational influence on passing objects could in principle reveal them, and in the sparsely populated spaces between stars. Such close encounters are rare, but some stellar mass black holes have companions. When 2 massive stars form together in a binary system, they evolve together. The more massive star exhausts its fuel first, explodes in a supernova, and potentially collapses to form a black hole, while its companion continues burning. The result is a binary system containing 1 living star and 1 black hole. And if the companion star is close enough, the black hole's gravity can begin to pull material from its outer layers, gas flowing from the companion star toward the black hole, spiraling into an accretion disk, heating to extreme temperatures, glowing brilliantly in X-rays. These systems are called X-ray binaries, and they are some of the most luminous objects in the galaxy. Cygnus X1, located approximately 6,000 light-years from Earth, was the first cosmic X-ray source to be widely accepted as containing a black hole. It was discovered in 1964, before the theoretical framework for black hole astrophysics was fully developed. For years it was debated. 2 of the most prominent physicists of the 20th century, Stephen Hawking and Kip Thorne, made a famous wager about it in 1974. Hawking bet that Cygnus X1 was not a black hole. He later conceded the bet, paying Thorne a subscription to a magazine. The black hole in Cygnus X1 has a mass approximately 21 times that of our Sun. Its companion is a blue supergent star, perhaps 40 times the mass of our Sun. The 2 orbit each other every 5.6 days, at a distance of only a few tens of millions of kilometers. The black hole pulls gas from the surface of the companion continuously. The gas spirals into an accretion disk glowing in X-rays detectable from Earth across 6,000 light-years of space. This system has been burning in the galaxy for hundreds of thousands of years, the companion star slowly losing its outer layers to the black hole, the black hole slowly gaining mass, an exchange measured across geological timescales. Patient, continuous, without urgency. V404 Cygni, another X-ray binary system, approximately 8,000 light-years away, contains a black hole of approximately 9 solar masses. This system is notable because it undergoes occasional outbursts, periods when the accretion rate suddenly increases dramatically. The disk brightens to extraordinary luminosity for days or weeks, then fades back to quiescence. The most recent outburst was in 2015, briefly making V404 Cygni the brightest source of high-energy X-rays in the sky, 8,000 light-years away, and briefly outshining everything else visible at those wavelengths. The black hole announcing itself across the galaxy with a flare and then settling back into its usual darkness. Patient, ancient, waiting. To truly understand black holes, you have to understand something about the nature of space and time themselves. In ordinary experience, space and time seem completely different things. Space is where objects are. It has 3 dimensions. You can move through it in any direction. You can choose to go left or right, forward or backward, up or down. Movement through space is something you can control. Time is when events happen. It has 1 dimension. It moves only forward. You cannot choose to go backward in time, or stay still in time, or accelerate your progress through time in the way you can accelerate your progress through space. Space seems like a stage. Time seems like a river. Einstein showed that this intuition, while useful for everyday life, is profoundly misleading at a fundamental level. Space and time are not separate things. They are aspects of a single 4-dimensional structure, called space-time. This is not a metaphor, not an analogy. It is the mathematical framework within which all of modern physics operates, and within which all experimental results concerning gravity, motion, and the behavior of light find their most accurate description. In space-time, the division between space and time is not fixed. It depends on your state of motion. 2 observers moving relative to each other will disagree about how much of a particular interval is spatial and how much is temporal. Their space-time measurements will be different in a way that is precisely described by the mathematics of special relativity. Gravity, in Einstein's general relativity, is not a force in the traditional sense. It is a curvature of space-time, produced by the presence of mass. A massive object does not reach across space and pull on other objects. It curves the space-time around it, and other objects moving through that curved space-time follow paths that are the straightest possible lines in that curved geometry. These paths are called geodesics, from the perspective of an object following a geodesic. It is moving in a straight line, not being pulled by any force, simply taking the most direct path through the curved space-time it inhabits. What looks like the curved path of a planet orbiting the Sun, or an apple falling toward the Earth, is actually the straightest possible path through curved space-time. Near a black hole, the curvature of space-time becomes extreme. The geodesics near the event horizon curve so severely that no outward directed path, no matter how fast you travel, can escape the inward pull. Even light, traveling along the straightest possible path through space-time at the maximum speed the universe allows, follows geodesics that curve inward past the event horizon. Inside the event horizon, the curvature of space-time is so extreme that all geodesics, all possible paths through space-time for any object, lead inexorably toward the singularity. Movement in the direction of the singularity becomes as inevitable as movement forward through time. You cannot stop moving toward the singularity any more than you can stop time from passing. The geometry of space-time itself makes it unavoidable. The concept of space-time curvature is often illustrated with the image of a rubber sheet stretched flat and then deformed by a heavy ball placed on it. A smaller ball placed on the sheet rolls toward the heavy one, following the curved surface. This is a useful analogy, but it has a serious limitation. The rubber sheet exists in 3-dimensional space and curves downward into that space, implying there is a 3rd spatial dimension for it to curve into. Real space-time is 4-dimensional and curves within itself, without needing any external higher dimensional space to curve into. The mathematics describes this through a quantity called the metric tensor, which encodes how distances are measured at every point in spacetime. Near a massive object, the metric tensor changes in ways that produce what we experience as gravitational attraction. Near a black hole, the changes are so extreme that the metric tensor becomes singular at the event horizon in certain coordinate systems. Though this singularity in the coordinates is a mathematical artifact rather than a physical one, the physical singularity is at the center, not at the horizon. The mathematics of general relativity has been verified to extraordinary precision in environments ranging from the solar system to neutron star binaries to the mergers of black holes detected in gravitational waves. In every test, it has passed. The curvature of space-time is not a theoretical abstraction. It is the mechanism by which gravity operates throughout the observable universe. Time flows in one direction. This statement seems obvious, self-evident, a basic fact of experience so universal that it rarely invites examination. You remember the past. You do not remember the future. Broken cups do not spontaneously reassemble. Heat flows from hot to cold, never the reverse. Processes run in one direction and not the other. This directionality of time, the fact that the past and future are fundamentally different in ways that space directions are not, is called the arrow of time. And here is one of the deepest puzzles in physics. The fundamental laws of nature, at the microscopic level, are almost entirely time-symmetric. The equations governing the motion of particles, the equations of electromagnetism, the equations of quantum mechanics, work equally well in both temporal directions. If you filmed two particles interacting and played the film backward, the reversed interaction would be just as physically valid as the forward one. There is no microscopic arrow of time. The fundamental laws do not distinguish between past and future, and yet the macroscopic world has an unmistakable arrow of time. Eggs break, but do not unbreak. Stars burn, but do not unburn. The universe expands but does not contract, at least not yet, and not in any region we can observe. Physicists attribute the macroscopic arrow of time to the second law of thermodynamics, and specifically to the fact that the early universe began in a state of extraordinarily low entropy, extraordinarily high order, and has been evolving toward higher entropy, greater disorder ever since. The arrow of time is fundamentally a statement about the initial conditions of the universe, not about the underlying laws themselves. Black holes enter this picture in a profound way. When matter falls into a black hole, its entropy increases. The second law of thermodynamics is satisfied. But when Hawking radiation was discovered, a paradox emerged. The radiation appeared to be perfectly thermal, maximally entropic, carrying no information. If the radiation carries no information about what fell in, then as the black hole evaporates, the total entropy of the observable universe might decrease when the information locked inside the black hole disappears. This would violate the second law of thermodynamics. The connection runs deep. The arrow of time, the second law, information conservation, the nature of black hole evaporation. All of these seemingly separate topics turn out to be aspects of the same fundamental puzzle, a puzzle that sits at the intersection of thermodynamics, quantum mechanics, and general relativity, the three pillars of modern physics, each tested to extraordinary precision within its domain, each producing apparently contradictory implications when applied to black holes. The black hole is not merely an exotic astronomical object. It is a lens through which the deepest questions about the nature of reality become visible. Not all black holes are the same. The simplest description of a black hole, called the Schwarzschild solution, describes a perfectly spherical, non-rotating black hole. A single parameter, mass, determines everything about it. But real black holes form from spinning stars, and the angular momentum of the original star is conserved during the collapse. A spinning star collapses to a spinning black hole. A rotating black hole is described by a different solution to Einstein's equations. Discovered in 1963 by the New Zealand mathematician Roy Kerr. The Kerr solution describes a black hole characterized by two parameters, mass and spin. And a rotating black hole is a fundamentally different object from a non-rotating one, not just quantitatively, but qualitatively. A non-rotating black hole has a single special surface, the event horizon. A rotating black hole has two, The outer surface is called the ergosphere. It is not the event horizon. Objects inside the ergosphere can still escape, but they cannot remain stationary. They are dragged along in the rotation of spacetime itself. This dragging of spacetime by a rotating mass is called frame dragging, or the lens-thirring effect. It occurs to some degree around any rotating mass. The Earth is rotating, and its rotation very slightly drags the spacetime around it, an effect measured by a satellite called Gravity Probe B launched in 2004. Near a rotating black hole, frame dragging becomes extreme. Inside the ergosphere, spacetime itself is dragged in the direction of the black hole's rotation faster than the speed of light. This does not violate relativity because it is spacetime that is moving, not an object within spacetime. But the consequence is real and remarkable. Any object inside the ergosphere is dragged along with the rotating spacetime. It cannot resist this rotation. It cannot remain pointing in a fixed direction relative to distant stars. Spacetime itself forces it to rotate. There is a mechanism called the Penrose process, named after the physicist Roger Penrose, who described it in 1969, by which energy can actually be extracted from a rotating black hole. An object entering the ergosphere can split into two pieces. One piece falls into the black hole carrying negative energy. The other escapes with more energy than the original object had before it entered. The extra energy comes from the rotational energy of the black hole, which is reduced by the process. In principle, a rotating black hole is a vast reservoir of energy that can be extracted. Up to 29% of the total mass energy of the black hole can be stored in its rotation and in principle extracted. Astrophysicists believe that the powerful jets produced by quasars and active galactic nuclei, jets that can extend for millions of light years, may be powered by exactly this mechanism, operating at enormous scales over cosmological timescales. The universe extracting rotational energy from spinning black holes to power some of its most spectacular displays. Gravity and rotation, working together. Across billions of years of cosmic time, the maximum spin rate of a black hole is limited by physics. What would happen if you tried to spin a black hole faster than its maximum rate? The answer involves an interesting theoretical constraint. A black hole spinning at its maximum rate has its event horizon and its singularity in a specific geometrical relationship. If you added more angular momentum beyond this maximum, the event horizon would shrink to zero size, leaving the singularity exposed. An object called a naked singularity. A singularity without any event horizon surrounding it. Roger Penrose proposed that this cannot happen, that the laws of physics somehow always prevent naked singularities from forming. This conjecture is called cosmic censorship. The universe censoring its own singularities, hiding them inside event horizons away from the outside world. Whether cosmic censorship is strictly true in all cases remains an open mathematical question. There are theoretical solutions to Einstein's equations that appear to produce naked singularities. But whether these solutions can actually form from physical initial conditions through realistic physical processes is not settled. The universe may be protecting something, or the mathematics may be telling us something we do not yet fully understand about the behavior of matter at extremes that no physical process can actually achieve. Light near a black hole does not behave the way light behaves anywhere else. This is one of the first observational confirmations of general relativity. The bending of light by gravity, predicted by Einstein and confirmed during the solar eclipse of 1919. When Arthur Eddington measured the positions of stars near the edge of the Sun during totality and found them shifted exactly as Einstein predicted. That result made front-page news around the world, made Einstein famous overnight, confirmed that space itself curves in the presence of mass. Near a black hole, this light bending becomes extreme beyond anything observable in the solar system. At twice the Schwarzschild radius, the light bending is already dramatic. Light from distant objects is distorted into arcs and rings. Multiple images of the same source can appear around a black hole. A source directly behind the black hole can appear as a complete ring of light surrounding it, an Einstein ring. At exactly 1.5 times the Schwarzschild radius, something extraordinary happens. Light can orbit the black hole, not fall in, not escape, Orbit. This is called the photon sphere. The radius at which the gravitational pull of the black hole provides exactly the centripetal acceleration needed to keep light moving in a circular orbit. In principle, a photon entering the photon sphere at exactly the right angle could orbit the black hole indefinitely, traveling in a circle at the speed of light, never approaching closer, never escaping farther. In practice, this orbit is unstable. The slightest perturbation causes the photon to spiral either inward toward the event horizon or outward into free space. But the photon sphere is real. It is one of the exotic features visible in simulations of black hole environments, contributing to the complex patterns of light distortion around rotating and non-rotating black holes alike. The image of M87 captured in 2019, the first direct black hole image, shows the bright ring of the accretion disk and the dark shadow at the center. The boundary of the shadow is related to the photon sphere, the innermost edge of the region from which no light reaches the observer, not the event horizon itself, but a slightly larger region, the photon capture radius. The black hole we see in that image is not the event horizon. It is the shadow, defined by where light bends so severely that it falls into the black hole rather than reaching our telescopes. Light that barely misses falling in, that passes just outside the capture radius, is bent dramatically, looping partway around the black hole before escaping, carrying to our detectors the image of regions of space on the far side of the black hole. A telescope pointed at a black hole sees, in the most energetic regions near the photon sphere, multiple copies of the entire surrounding universe, bent and distorted and layered around the central shadow, the dark center surrounded by light from everywhere else. The universe has been around for 13.8 billion years, and in that time, gravity has been working on every scale, from the smallest molecular clouds to the largest cosmic structures, drawing matter together, building stars, building black holes, building galaxies. The most distant objects we can see are also among the oldest, because the light from them has been traveling toward us since the very early universe. The most distant quasars, the most distant actively feeding supermassive black holes, are seen as they were when the universe was less than 1 billion years old, less than 7% of its current age. And yet they already contain black holes of billions of solar masses. This is deeply puzzling. A black hole cannot grow faster than the Eddington rate, the rate at which radiation pressure from the accretion disk pushes back against infalling matter and limits further consumption. Growing from a stellar mass seed to 1 billion solar masses at the Eddington rate requires continuous feeding for hundreds of millions of years. But the universe was less than 1 billion years old when some of these enormous black holes already existed. For them to have grown so large so quickly, they would need to have started from massive seeds and fed continuously at or above the Eddington limit for essentially their entire existence. How the very first black holes formed, what seeds they grew from, how they accumulated mass so rapidly in a young universe, is one of the most actively investigated questions in modern astrophysics. One possibility involves the direct collapse of massive primordial gas clouds. In the early universe, regions of dense gas might have collapsed directly into black holes, with initial masses of 10,000 to 100,000 solar masses, without first forming stars, providing the massive seeds needed for rapid growth. Another possibility involves runaway stellar mergers. In the dense star clusters of the early universe, stars colliding and merging repeatedly, building up to masses of thousands of solar masses before collapsing to form massive black hole seeds. A third possibility involves the merger of smaller black holes. Gravitational wave observations suggest that black hole mergers are common. Perhaps in the dense environments of the early universe they were far more frequent, allowing small black holes to merge repeatedly and build up to large masses quickly. None of these scenarios has been definitively confirmed. The first massive black holes, the seeds of the supermassive monsters at the centers of today's galaxies, remain one of the great unsolved origin stories of cosmic history, the universe knowing how the story ended, and keeping the beginning to itself. There is an idea in modern theoretical physics so strange, so counterintuitive, so resistant to easy visualization, that even the physicists who work with it professionally sometimes pause to appreciate its strangeness. The holographic principle. It emerged from the study of black hole thermodynamics in the 1970s and 1980s, from work by Jacob Bekenstein and Stephen Hawking on the entropy of black holes. Entropy is a measure of the number of microscopic states that correspond to a given macroscopic state. The higher the entropy, the more ways the microscopic constituents of a system can be arranged while still producing the same large-scale appearance. Bekenstein showed that the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This was deeply surprising. For ordinary objects, entropy scales with volume. Double the volume, double the entropy. The information content of a system is stored throughout its three-dimensional extent. But for a black hole, the information content scales with the two-dimensional surface area of the horizon, not the three-dimensional volume it encloses. This suggests something extraordinary, that the information describing everything inside the black hole, everything that has ever fallen through the horizon, is somehow encoded on the two-dimensional surface of the event horizon itself, not inside, on the surface, like a hologram, where a three-dimensional image is encoded in a two-dimensional pattern on a flat surface. Gerard 't Hooft and Leonard Susskind developed this into a general principle, suggesting that the holographic nature of black holes might be a feature of reality in general, not just of black holes, that the three-dimensional universe we inhabit, with all its objects and structures and complexity, might be in some deep mathematical sense equivalent to information encoded on a two-dimensional surface. The holographic principle was made mathematically precise in 1997 by Juan Maldacena, in a framework called the ADS-Shift correspondence, anti-de Sitter space conformal field theory correspondence. This framework provides a precise mathematical dictionary between a theory of gravity in a three-dimensional space and a quantum field theory without gravity on the two-dimensional boundary of that space. The two descriptions are equivalent, exactly, completely, in every mathematical detail. A three-dimensional gravitational theory, perfectly equivalent to a two-dimensional non-gravitational theory. The implications are profound and still being worked out. It suggests that gravity itself, the curvature of space-time, the phenomenon that shapes the largest structures in the universe, may emerge from quantum mechanical processes happening on a lower dimensional surface. That space itself, as we experience it, may be emergent, not fundamental. That the three-dimensional world may be, in some deep sense, a projection, not an illusion. The physics is real. The experiences are real. The objects are real. But the three-dimensionality may be a kind of encoding rather than a fundamental feature of reality. The universe telling us something about its own structure that we are still learning how to hear. The ADS-Shift correspondence has become one of the most studied frameworks in theoretical physics since its discovery. A striking consequence of the holographic principle is that it may provide a way to calculate properties of strongly interacting quantum systems by mapping them to a gravitational theory in one higher dimension. This has found applications not just in theoretical physics, but in condensed matter physics, and the study of exotic states of matter where the quantum mechanical interactions are too strong for conventional methods to handle. The quark-gluon plasma produced in heavy ion colliders at CERN and Brookhaven behaves in ways that are difficult to calculate directly, but find natural descriptions in terms of the dual gravitational theory through the ADS-Shift correspondence, a theory of black holes in higher dimensions, providing insight into the behavior of matter in laboratories on Earth. The connections run in unexpected directions, and each connection suggests that the holographic principle reflects something deep and true about the structure of reality, something whose full implications are still unfolding. The holographic principle also connects to the question of what happens to information in a black hole. If the three-dimensional interior of a black hole is holographically equivalent to its two-dimensional horizon, then the information that fell in is encoded on the horizon surface, not lost inside a volume that ceases to exist upon evaporation, but preserved in the pattern of correlations on the surface, radiating away as subtly correlated Hawking radiation. This perspective suggests that the information paradox may be resolved not by some exotic new physical process, But by recognizing that the three-dimensional interior description and the two-dimensional surface description are equivalent encodings of the same information, the apparent loss of information being an artifact of using the wrong description. The black holes we have discussed so far formed from the collapse of massive stars. But there is a hypothetical class of black holes that may have formed in the very first moments of the universe, before any stars existed, before galaxies existed, before most of the structures we observe in the cosmos had any chance to form. Primordial black holes. In the first fractions of a second after the Big Bang, the universe was extraordinarily hot and extraordinarily dense. Matter and energy were compressed together in a state of almost incomprehensible intensity. In this environment, quantum fluctuations, random variations in the density of the early universe, could potentially produce regions of above-average density. If a region became dense enough, it might collapse directly to form a black hole, before the matter had any chance to organize itself into atoms or stars. The masses of primordial black holes would depend on when they formed. Black holes forming in the first fraction of a second after the Big Bang might have masses as small as the Planck mass, approximately 22 micrograms. About the mass of a grain of sand, but compressed to the smallest scale quantum mechanics allows. Black holes forming slightly later might have masses ranging from asteroids to stars to many solar masses, depending on the size of the region that collapsed. Primordial black holes remain hypothetical. No confirmed observation of one has been made, but they are theoretically interesting for several reasons. First, they represent a possible explanation for some of the dark matter in the universe. If a sufficient number of primordial black holes formed in a certain mass range, their combined gravitational effects could account for some or all of the dark matter we infer from galactic rotation curves and other observations. Second, the smallest primordial black holes, those with masses smaller than about 10 trillion kilograms, would have evaporated by now through Hawking radiation, their entire mass converted to radiation and particles over the lifetime of the universe, providing a possible observational test for Hawking radiation itself. If these tiny black holes existed and evaporated, they would have left detectable signatures in the distribution of gamma-ray bursts across the universe. Third, primordial black holes represent a genuinely different kind of black hole, one not formed by stellar evolution, not connected to any galaxy or star system, formed instead from the raw quantum fluctuations of the earliest universe, carrying a direct imprint of conditions that existed in the first moments of everything. The search for primordial black holes, through gravitational microlensing, through gravitational wave observations, through searches for evaporation signals, is ongoing. The universe formed in an instant of extraordinary density, and it may have left behind small dark objects drifting through space for billions of years, patient witnesses to the very beginning. The gravitational microlensing searches for primordial black holes have placed significant constraints on what fraction of dark matter they could constitute. If primordial black holes in certain mass ranges constituted all of the dark matter, we would expect to see characteristic patterns in the brightness variations of stars in nearby galaxies as the black holes passed between us and those stars. Current surveys have not found evidence of such patterns in the mass ranges most sensitively probed, suggesting that primordial black holes in those ranges cannot account for all of the dark matter. However, there remain mass windows where the constraints are weaker, and primordial black holes remain viable dark matter candidates. The mass range around asteroid mass primordial black holes is particularly interesting, because it is difficult to probe with current techniques. Future gravitational wave detectors and space-based microlensing surveys may close or confirm this window in the coming decades. Nobody has ever been inside a black hole. No probe has transmitted data from within an event horizon. No theoretical framework has been confirmed by observation beyond it. The interior of a black hole is, in the most literal scientific sense, unknown. But theory has things to say about it, and those things are strange in ways that take time to absorb. Outside the event horizon, space-time is curved, but still recognizably space-time. Objects can move in any spatial direction. Time flows forward. The future is different from the past. The structure is familiar in its basic geometry even if locally distorted. Inside the event horizon. According to general relativity, the structure of space-time undergoes a fundamental change. The radial direction, the direction pointing toward the singularity, becomes time-like. This means that movement toward the singularity becomes not a spatial journey, but a temporal one. Not movement through space, but movement through time. And you cannot stop moving through time. You cannot reverse your movement through time. You cannot hover in place while time passes. Inside a black hole, you cannot stop moving toward the singularity. It is not that the singularity pulls you with some irresistible force. It is that the singularity is in your future, and you cannot avoid your future any more than you can avoid tomorrow. For a non-rotating black hole, the interior is relatively simple in its geometry. A radially infalling observer reaches the singularity in a finite proper time after crossing the horizon. For a stellar mass black hole, this time is microseconds. For a supermassive black hole of several billion solar masses, it could be hours or days of proper time. For a rotating black hole, the interior geometry is dramatically more complex. The Kerr solution, which describes rotating black holes, has an interior structure with multiple surfaces and regions with strange causal properties. In the Kerr geometry, there is a region inside the inner horizon of the rotating black hole, where the singularity is not in the future, but appears to lie off to the side. A region where in principle you might avoid the singularity and pass through to a different region of space-time entirely. Physicists have speculated that this might represent passage to a different universe, or to a different region of the same universe far away in space and time. But this analysis is almost certainly incomplete. The interior of a rotating black hole, as described by the Kerr solution, is known to be unstable. Small perturbations cause it to deviate dramatically from the exact Kerr geometry. A real infalling observer, with finite mass and charge and radiation, would modify the geometry around them as they fell, potentially changing the interior structure significantly. What actually happens deep inside a rotating black hole, whether the exotic structures of the Kerr interior survive in any physical sense, is not known. The interior of a black hole remains genuinely, completely beyond our current reach. A sealed room in the structure of the universe, the door locked by the laws of physics themselves. In the early 1970s, a series of theoretical results emerged that revealed an unexpected and beautiful connection between black holes and thermodynamics. The 4 laws of thermodynamics, developed over the 19th century to describe the behavior of heat and energy, have precise analogues in black hole physics. The 0th law of thermodynamics states that a system in thermal equilibrium has a uniform temperature throughout, for black holes. The analogous statement is that a stationary black hole has a uniform surface gravity across its entire event horizon, just as temperature is uniform in equilibrium. Surface gravity is uniform over a static or stationary horizon. The 1st law of thermodynamics states that energy is conserved. That changes in the internal energy of a system equal heat added minus work done. For black holes, there is a precise analogy relating changes in the mass of the black hole to changes in its area, its angular momentum, and its charge. The 2nd law of thermodynamics states that entropy never decreases in an isolated system. For black holes, the area theorem proved by Hawking in 1971 states that the total area of event horizons in any process never decreases, just as entropy never decreases. The 3rd law of thermodynamics states that absolute zero temperature cannot be reached in a finite number of steps. For black holes, the analog is that a black hole cannot be reduced to zero surface gravity in a finite number of steps. At first, these were considered formal mathematical analogies, beautiful correspondences, but not necessarily physically meaningful. Then Hawking radiation changed everything. Hawking radiation is genuinely thermal. It has a real temperature. A black hole actually radiates like a black body at a temperature inversely proportional to its mass. For a stellar mass black hole, this temperature is unimaginably small, a fraction of a billionth of a degree above absolute zero. But it is a real temperature, not an analogy. And this means the analogy between black hole area and entropy is not merely formal. The area of the event horizon is genuinely related to the thermodynamic entropy of the black hole. The entropy of a black hole is proportional to the area of its event horizon measured in units of the Planck area, the square of the Planck length, the smallest meaningful length scale in physics for a stellar mass black hole. This entropy is approximately 10 to the power of 77, incomparably larger than the entropy of the star that formed it. When a star collapses to form a black hole, the entropy of the universe increases by an extraordinary amount. The black hole is not a loss of order. It is an extraordinary creation of entropy. The connection between black hole physics and thermodynamics runs deeper than anyone initially expected. It suggests that thermodynamics, entropy, temperature, the arrow of time, are all connected to the geometry of spacetime in ways that are still being worked out. Black holes revealing the structure of reality at the junction of the largest and smallest scales. The deep connection between black hole thermodynamics and quantum information theory has become one of the most active areas in theoretical physics in recent years. The concept of entanglement entropy, the entropy associated with quantum correlations between a region and its complement, has been found to obey relations that mirror the Bekenstein-Hawking formula for black hole entropy in certain theories where the ADS-C-Fift correspondence applies. The entropy of a region in the quantum field theory on the boundary can be calculated by finding a minimal surface in the dual gravitational spacetime. This formula, called the Ryuta-Kayanagi formula, connects the geometry of spacetime directly to the entanglement structure of the dual quantum system, suggesting that spacetime geometry itself emerges from quantum entanglement. The geometry of space, the separation between points, the way that regions are connected, may be a consequence of how quantum information is organized across the quantum mechanical degrees of freedom that underlie reality. Black holes are among the most permanent structures the universe creates. Stars burn out, in billions of years for the smallest, in millions for the largest. Planets cool and erode, and are eventually absorbed by their dying stars. Galaxies merge and transform over billions of years. The universe itself evolves continuously. The structures and arrangements we see today are temporary configurations in an ongoing process of change. But black holes persist. They do not burn fuel. They have no internal pressure to maintain against gravity, no process consuming their structure from within. A black hole simply exists, defined entirely by its mass, spin, and charge, maintaining these properties indefinitely as long as nothing falls in and nothing escapes. And for the vast majority of the universe's future history, almost nothing will fall in. The universe is expanding. Galaxies are moving apart. The density of matter is decreasing. The accretion of material onto black holes, already slow compared to the early active quasar epoch, will slow further and further. Black holes will persist in the dark, long after the stars have gone. The last stars, red dwarfs burning slowly on their hydrogen reserves, will exhaust their fuel in approximately 10 to the power of 14 years, 100 trillion years from now, long after the sun has become a white dwarf and cooled to darkness. After the last stars go dark, the universe will be populated primarily by black holes, neutron stars, and cooling white dwarfs. Separated by expanding voids in an increasingly cold and dark cosmos, the white dwarfs will eventually cool completely to black dwarfs. Dark, cold, inert, barely distinguishable from the blackness around them. The neutron stars similarly, the black holes will remain through timescales that make the current age of the universe seem like an instant. The black holes will drift in the dark, slowly evaporating through Hawking radiation at rates so slow that the process is effectively imperceptible across any timescale currently meaningful. A stellar mass black hole takes approximately 2 times 10 to the power of 67 years to evaporate. As we noted earlier, this is not a year count that can be made intuitive by any comparison currently available to human experience. A supermassive black hole of several billion solar masses would take dramatically longer, approximately 10 to the power of 96 years. But eventually, given enough time, even these will evaporate. The last black hole in the observable universe, radiating its final particle of Hawking radiation, diminishing, dimming, until nothing remains. After that event, the universe will contain nothing but the faintest thermal radiation at a temperature so close to absolute zero that the difference is unmeasurable. Perfect equilibrium, complete entropy, maximum disorder in the thermodynamic sense. This state is called the heat death of the universe, and it lies so far in the future that describing it in years requires a number with more digits than there are atoms in the observable universe. The black holes will be the last lights, fading, very slowly, in the final dark. The progression from a star-filled universe to a black hole-dominated universe to a universe of evaporating remnants to the final heat death is called the far future of the universe by cosmologists. It represents one of the most extraordinary extrapolations of known physics ever attempted, starting from established principles of thermodynamics, quantum mechanics, and general relativity, and extending them forward in time by factors that dwarf the current age of the universe by incomprehensible amounts. The extraordinary thing is not that we can make these predictions. It is that the underlying laws of physics that make them possible were discovered through observations confined entirely to the first 14 billion years of cosmic history. Laws that apparently extend with full validity across a time span billions of times longer than the period over which they were discovered. The universe operating by rules as patient as the black holes they describe. Everything we have explored tonight, every fact about black holes, every mystery, every connection between gravity and quantum mechanics and thermodynamics and information, points toward something that is not about black holes at all. It points toward the nature of understanding itself. Black holes are the places in the universe where our knowledge ends, where the two greatest theories in physics fail to agree, where mathematics produces infinities that signal the incompleteness of our models, where the questions we can ask outrun the answers we possess. In one sense, this is humbling. We have mapped the cosmic microwave background to extraordinary precision. We have detected gravitational waves from collisions a billion light-years away. We have measured the expansion rate of the universe, sequenced genomes, split atoms, built machines that think, landed humans on the moon, and yet the center of a black hole, a structure that forms reliably from the collapse of massive stars, a process that has been happening throughout the observable universe for billions of years, remains beyond the reach of our understanding. But in another sense, the boundaries of knowledge are among the most beautiful things about the pursuit of understanding. Every limit of current theory is a door. Every infinity produced by an equation is a signal that something new lies beyond. Every paradox is an invitation. The information paradox, the singularity, the origin of supermassive black holes, the nature of Hawking radiation, the connection between gravity and quantum mechanics. These are not embarrassments. They are frontiers. They are the places where physics is most alive, where new ideas are being tested and contested and revised, where the framework of understanding is being actively extended. And the people working on these questions are doing something that every generation of scientists has done before them, standing at the edge of what is known, looking into the dark and trying to see further. The history of physics is the history of this process. Newton looking at the orbit of the moon and the fall of an apple and seeing the same force at work. Einstein looking at the perihelion of Mercury and the constancy of the speed of light and finding a new geometry of space-time. Planck looking at the spectrum of radiation from hot objects and finding that energy must come in discrete packets. Each advance came from exactly the places where existing theory failed. The singularity at the center of a black hole is pointing toward something. The information paradox is pointing toward something. The holographic principle is pointing toward something. We do not yet know what, but the pointing is clear, and the direction is forward, into the dark, toward the next understanding. With the same patient curiosity that has driven the expansion of human knowledge since the first person looked up at a night sky and wondered what was there. The black holes are waiting, patient as always, at the edge of what we know, holding their secrets, until we are ready to understand them. There is a quality to black holes that no other object in the universe possesses: perfect silence, Not the silence of a quiet room, not the silence of an empty field at night, not even the silence of deep space between the stars. A more fundamental silence than any of those. The silence of a place from which no signal of any kind can escape, where no vibration, no radiation, no gravitational wave, no information whatsoever can carry word of what is happening to any observer outside. A perfect informational silence. The surface of the sun is turbulent and loud in every sense that physics allows. Granules of convecting plasma the size of Texas rise and fall constantly. Magnetic field lines tangle and snap in events that release the energy of billions of nuclear bombs. Solar flares and coronal mass ejections blast material into space at millions of kilometers per hour. All of this activity announces itself in light, in radio waves, in the charged particles of the solar wind that reach Earth and create auroras at the poles. A neutron star is similarly expressive, spinning pulsars, sweeping their beams across the galaxy with metronomic regularity. Magnetars crackling with starquakes that briefly affect Earth's ionosphere from 50,000 light-years away. Even the most distant galaxies announce themselves across the universe, their light traveling for billions of years to reach our telescopes, carrying information about their composition, their age, their motion through space. Everything in the universe communicates, except what lies beyond an event horizon. Inside a black hole, events occur. The infalling matter continues its journey toward the singularity. Interactions happen. The geometry of space-time evolves in extraordinary ways, all of it governed by the same physical laws that govern everything else, and none of it can send any word outward. The event horizon is the universe's most perfect wall of silence, not built of any material, not maintained by any force, simply the consequence of geometry, of a curvature so extreme that the straightest possible path through space-time leads inward rather than outward. The universe organizing itself in such a way that some regions are permanently and absolutely cut off from communication with others. And yet we know they are there. We know they are real. We know they contain matter and geometry and the ongoing operation of physical law. We know all of this from the outside, from the effect the silence has on the space around it. The way a deep silence in a room sometimes tells you more than sound would. The way the absence of a thing can define the presence of something else entirely. The black hole is defined by what it withholds. And in withholding everything, it tells us something extraordinary about the nature of the universe that contains it. The silence of a black hole is not the silence of absence. It is the silence of absolute containment. Consider the difference between a room that is quiet because nothing is happening in it, and a room that is quiet because something is happening in it that cannot make any sound. The first is empty. The second contains a world. The interior of a black hole is like the second room. Events are occurring. Geometry is evolving. Matter is falling. The laws of physics are operating fully, and none of it reaches the outside. In ordinary physics, information propagates. Information about the state of any system spreads outward over time in ripples of light and gravity and quantum correlations. The universe is in this sense deeply interconnected, all of its parts in constant implicit communication. But inside a black hole, this communication is cut, in one direction at least. Nothing inside the horizon can communicate outward. The universe becomes divided, a part of it sealed away from communication with the rest, in a way that nothing else in nature achieves. The universe was not always as it is tonight. Tonight, the sky appears relatively calm. The Milky Way a gentle spiral, stars distributed across it in patterns that seem almost serene compared to what came before. The early universe was different. In the first 100 million years after the Big Bang, the universe was dark. Not the dark of a clear night with stars scattered across it, a genuine darkness. The darkness that preceded the first light. Hydrogen and helium, the products of Big Bang nucleosynthesis, drifted through expanding space in vast, slow clouds, cooling as the universe expanded, beginning to collapse under gravity into the first structures. These first structures were not galaxies, not solar systems. They were dense knots of dark matter, gravitational seeds around which the baryonic gas slowly gathered. The gas collapsed, heated, began to fragment, and the first stars ignited. These first stars, called population 3 stars, were unlike anything that exists in the universe today. They formed from gas that was almost entirely hydrogen and helium, with essentially no heavier elements, no carbon, no oxygen, no nitrogen, no iron. Without these heavier elements to radiate away heat efficiently, the collapsing gas clouds fragmented into larger pieces than present-day star formation produces. The result was stars of extraordinary mass, some estimated to be hundreds or even thousands of times the mass of our Sun. These were the most massive stars the universe has ever contained. They burned with ferocious intensity, ionizing the hydrogen around them, flooding the young universe with ultraviolet radiation, beginning the process called reionization, transforming the neutral hydrogen that had filled the universe after the Big Bang into the ionized plasma that fills the intergalactic medium today. And they burned out quickly. Stars of such extraordinary mass live for only a few million years, perhaps less. When they died, they did not become supernovae in the conventional sense. The most massive population 3 stars likely collapsed directly to black holes. The entire stellar mass, hundreds of solar masses, falling inward without the dramatic explosive rebound that characterizes supernova events in less massive stars. Silent collapses. No supernova, no planetary nebula, no scattering of enriched material across light years. Just enormous stars, burning briefly in the primordial dark, and then collapsing quietly into the first black holes. These first black holes seeded the formation of supermassive black holes at the centers of the first galaxies, merging with each other and accreting material over billions of years to become the monsters we observe at galactic centers today. The quiet at the center of the Milky Way, the dormant Sagittarius A star sitting patiently at the galactic core, has its origin in those first silent collapses in the early universe, before the first planet formed, before the first ocean, before the first cell divided, in the darkness before any star had yet lived and died. The transition from the dark ages of the universe to the epoch of reionization is one of the most dramatic phase transitions in cosmic history. After the Big Bang, the universe was initially so hot and dense that matter was ionized plasma, free electrons and protons mixed in a sea of radiation. As the universe expanded and cooled, it reached a temperature where electrons and protons could combine to form neutral hydrogen atoms. This happened approximately 380,000 years after the Big Bang. In an event called recombination, the universe became transparent for the first time. Light could travel freely. The cosmic microwave background radiation we detect today is the light from this moment, the first light that was able to travel freely through the cosmos. After recombination, the universe entered the dark ages, neutral hydrogen and helium, cooling slowly. No stars, no galaxies, no sources of light. The first stars ended the dark ages. Their radiation ionized the surrounding hydrogen, starting a process that spread through the universe over hundreds of millions of years, until essentially all of the hydrogen in the intergalactic medium had been reionized. The first stars and their black hole descendants transforming the universe from dark and neutral to luminous and ionized. The mathematics of black holes is less than a century old, but the intuition that very massive objects might trap light, that gravity might be powerful enough to prevent escape, is older than general relativity by more than a century. In 1783, the English clergyman and amateur scientist John Michell reasoned from Newton's law of gravity and the corpuscular theory of light, then the dominant view that a sufficiently massive star would have an escape velocity greater than the speed of light. He called these objects dark stars. A star massive enough that light could not escape, would be invisible, present only through its gravitational influence on nearby objects. Michell presented this idea to the Royal Society of London. His paper was largely forgotten for nearly 2 centuries. In 1796, the French mathematician Pierre-Simon Laplace independently reached the same conclusion, including a calculation in his influential work on celestial mechanics. He too called them dark bodies, and he too was largely ignored on this particular point. The idea lay dormant until Einstein's general theory of relativity in 1915, provided the mathematical framework within which the modern understanding of black holes would develop. Karl Schwarzschild, working at the Russian front during World War I, solved Einstein's equations exactly for the case of a spherically symmetric massive object just months after Einstein published the theory, producing what is now called the Schwarzschild solution. Schwarzschild found that his solution had a peculiarity at a certain radius, now called the Schwarzschild radius, where the mathematics appeared to break down. Einstein himself initially believed this singularity in the mathematics meant that real physical objects could never be compressed to that radius, that nature would prevent it. He was wrong. Nature allows it, and does it regularly. Across the observable universe, the term black hole itself was not coined until 1967, when the American physicist John Wheeler used it in a lecture, and it immediately caught on, replacing the cumbersome descriptions that had been used before. 2 words, capturing something real and strange and permanent about the structure of the universe. What Michel glimpsed from Newton's equations in 1783, what Schwarzschild calculated in a trench in 1915, what Wheeler named in 1967, what the Event Horizon Telescope photographed in 2019, is the same object, discovered slowly, named reluctantly, accepted gradually, understood partially, still yielding its deepest secrets. The cultural history of our understanding of black holes reflects how humanity comes to terms with ideas that initially seem impossible. Every generation of scientists has had to revise its intuitions about what is physically possible. Einstein himself, whose equations predicted black holes, resisted the implication for years. He wrote a paper in 1939 arguing that black holes could not form in nature, that the collapse would always be halted before reaching the Schwarzschild radius. His argument was flawed. His conclusion was wrong. Even the greatest scientific mind of the 20th century needed time to accept the full implications of his own equations. Oppenheimer and Snyder in the same year showed through careful mathematical analysis that the collapse could proceed all the way to a black hole. Their work was initially not widely accepted. The community was not ready. Acceptance came slowly, through the work of many people, over many years, through the accumulation of theoretical understanding and eventually observational evidence. That is the normal pace of science, not a single dramatic revelation, but a gradual dawning, a reluctant but ultimately complete acceptance of what the evidence and the mathematics together require. Imagine a perfect sphere, not a physical object, not a ball of matter, a purely geometric surface, a boundary in space, the event horizon. From outside, this surface appears dark. No light escapes from it. The region of space beyond it is inaccessible to any external observer for any purpose. Communication with anything on the other side is impossible. And yet, from inside, looking outward toward the horizon, the geometry is strange in a different way. An observer falling freely through the event horizon of a sufficiently large black hole sees the outside universe, not blocked, not hidden, visible through the horizon as a shrinking circle of light overhead as they fall toward the singularity. This circle of light shows the entire outside universe compressed into a diminishing disk directly above. As the observer falls, the disk shrinks. The light from the outside universe becomes increasingly blue-shifted, more energetic, more concentrated, in the final moments before reaching the singularity. The entire history of the outside universe, from the moment the observer crossed the horizon to the final end of the cosmos, would flash by in the outside light, compressed into those last moments of proper time. Whether this is physically realizable, whether the increasing blue shift would create radiation intense enough to destroy the observer before the singularity is reached, is an open question that depends on the details of the black hole and the specific trajectory. But the geometry allows it in principle, an inside view of the universe playing out its entire remaining future in the final moments of a fall toward a singularity. Time inside the black hole running to its conclusion, while time outside continues for whatever remains of the universe's future. The geometry of general relativity producing scenarios so strange that they seem impossible, and yet they follow with mathematical necessity from equations that have been verified to extraordinary precision in every testable context. The universe does not restrict itself to scenarios that are easy for human minds to visualize. It follows its own mathematics, patient and indifferent, to wherever that mathematics leads, and sometimes it leads to places like this, where time and space exchange their usual roles, where the future lies in a particular direction, where the entire remaining history of the external universe is visible from inside, compressed by the curvature of space-time into a narrowing window of light overhead. Strange, yes, but genuinely how the universe is structured. The phenomenon of gravitational lensing by black holes produces some of the most visually extraordinary consequences in all of astrophysics. When a black hole passes between a distant star and an observer, the gravitational field of the black hole acts as a lens, bending the light from the background star, temporarily brightening it. This is called gravitational microlensing. The degree of bending and brightening depends on the mass of the lensing object and its distance, allowing astronomers to infer the mass even when the object itself is invisible. A black hole detected by its effect on light from a star it has never touched, not physically interacting with it, simply curving the space through which the light travels, and producing from that pure geometric effect a detectable brightening. That carries in its shape and duration information about the mass and distance of the invisible object. Pure gravity, pure geometry, announcing the presence of something that produces no light of its own, through the light of something else entirely. The universe finding a way to make the invisible legible, to make the silent speak, through the medium of light bent by the curvature of space. There is one more fact about black holes worth carrying into the quiet of this night. A fact not about their size or their temperature or their entropy or their singularities. A fact about their relationship to everything else. Black holes are not separate from the universe, not anomalies, not errors, not failures of nature to maintain order. They are the universe being entirely consistent with itself. Every black hole that exists because the laws of physics operate exactly as they do everywhere else. Gravity attracts. Conservation laws hold. The equations of general relativity that describe the bending of space-time around ordinary objects like the Sun and the Earth, extended without modification to more extreme situations, produce black holes as their natural consequence. Black holes are what the universe does when you apply its rules long enough and with enough mass. They are not exceptions. They are examples. The most extreme examples. The most dramatic examples. The examples that push every theory to its limit and reveal the places where our understanding is incomplete, but examples nonetheless, of the same forces and principles that hold atoms together, that keep planets in their orbits, that curve the path of light around the Sun in ways that were first measured on a May afternoon in 1919. The same universe, operating by the same rules, at scales and intensities that take the breath away, and from your position tonight, warm and still, held by the comfortable version of the same gravity that curves space-time to infinity at a singularity, surrounded by the atoms that were forged in the stellar predecessors of black holes across billions of years of cosmic history. You are not outside this story looking in. You are inside it, part of the same universe that contains the black holes, governed by the same laws, made of the same material, subject to the same forces at scales that are comfortable rather than extreme. The universe that produces black holes also produces this night, this quiet, this particular darkness that is warm and safe and full of the ordinary magic of a living world at rest. Both things at once, the extreme and the gentle, the violent and the peaceful, the incomprehensibly massive and the fragile and temporary. All of it the universe, in different expressions of the same underlying nature. And you, resting in the gentle version of a cosmos that also contains some of the most extreme objects that physics allows. Part of all of it. Every atom, every moment, every quiet breath in the dark. We have traveled far tonight. From the definition of a black hole, an object so dense that nothing escapes, to the birth of black holes in the collapse of massive stars, to the strange boundary of the event horizon, where time bends and information seals. From the 100 million invisible remnants drifting through our galaxy, to the supermassive giants at the centers of galaxies, including the quiet ancient mass at the heart of the Milky Way overhead tonight, from Hawking radiation and the slow evaporation of black holes across timescales, longer than the current age of the universe by incomprehensible factors, to the information paradox and the holographic principle, and the suggestion that the three-dimensional world may be encoded on a two-dimensional surface, from the first stars of the early universe and their silent collapses, to the fate of the last black holes in the far future of the cosmos, fading slowly in the final dark, from John Michel imagining dark stars in 1783, to the first photograph of a black hole's shadow in 2019. We have traveled through all of this together, at the slowest possible pace, the way the best journeys are made, and what remains after all of it is not anxiety or overwhelm or the particular vertigo that sometimes comes from contemplating things too large for the mind to hold comfortably. What remains is something quieter than that, a sense of the extraordinary scale of the universe you are part of, a sense of the patience at the heart of things, the black holes drifting in the dark for billions of years, the galaxies turning on timescales measured in hundreds of millions of years, the laws of physics operating without variation across the full 13.8 billion years of cosmic history. A sense that the universe is not in a hurry, that it has never been in a hurry, that its most dramatic structures spend the vast majority of their existence simply existing, simply persisting, simply being present in the dark, and a sense of your own place in all of it, not as something small and lost in an incomprehensible vastness, but as a specific and irreplaceable expression of the same universe that contains the black holes, made of the same material, governed by the same laws, temporary in the same way that all things are temporary, and present in the same way that all things are present. The black holes are out there tonight, in the dark between the stars, at the centers of galaxies, drifting through the intergalactic voids, in the data of every gravitational wave detector listening to the universe ring, patient, silent, ancient. And you are here, warm, briefly conscious, resting in the comfortable version of the same universe. Both things true at once. Both things part of the same story. Good night. The dark is patient, the universe is vast, and you are exactly where you belong.